How's it going, guys? Today in this video, we're going to be going over Module 1.1, Day 1, where we'll be talking about domain, range, and end behavior. Sorry. So before we get into that, though, I do want to remind you guys that there is a remind. How to suggest you guys join it. Just text at SLHS2ALG2 to 81010. It's on here on the board, or I guess on your screen. And we use it to remind you guys about tests and quizzes, and if we're changing homework assignments. And like last year as well, if you guys remember, the school did get shut down because of weather and COVID. So we do use Remind for that as well, to let you guys know what exactly you should be doing to stay up to date with class. So it is something useful in case anything happens last second that we couldn't account for. It's good to have those instant reminders onto your phone through Remind rather than waiting for us to update Canvas and get an email shout out to you guys and to your parents, all right? So let's keep on going. When you open your packet, the first thing you see is the calendar for this module, for Module 1. We have the published homeworks as well. I don't know why there's an 8 in packet, but it should just say packet. So it tells you, you know, the homework assignments, what numbers you should do, when the quizzes are, when the tests are, what the dates of that is going to be. So we do give you guys everything out laid out right here on, inside your packet. You will also see a full 6 weeks calendar on Canvas. If you go on there and look for that, you have the full 6 week calendar, including Module 2. But this right here is for Module 1, published homework, the page, all that good stuff. So let's keep on going. Start off with the lesson. Now we're going to begin 1.1 domain, talking about domain, range, and end behavior. So when we're representing an interval on a number line, and blank is a part of a number line without breaks, that's going to be your interval. An interval will be the part of a number line that doesn't have any breaks. So you have a number line like that, going from A to B. That right here between the two dots, that's going to be your interval. The interval from A to B is part of the number line that we didn't break from. Now, a blank interval has blank endpoints. That's going to be finite. A finite interval will have 2 endpoints, a beginning and an end. So it's finite because we can define the beginning and the end. And at the same time, those endpoints may or may not be included in the interval. It's going to depend on the interval itself. And then a blank interval is an unbounded at one or both sides, and that's going to be infinite. An infinite interval is unbounded or on one or both ends, or in other words, it doesn't have 2 endpoints. So one of those endpoints is going to negative infinity or positive infinity. So that means it's unbounded to one side. It's not closed off. It's not finite. You cannot define the beginning and end for an infinite interval. Set notation, the domain. This is what it says. You have the squiggly line X with the line, which stands for such that, with the inequality, same thing with the range. So that's going to be read as, we have the squiggly line X, such that X is greater than A, or whatever the inequality is. Right, so that X, it just says X, and that line stands for such that. So X, such that X is greater than A. It's really just your inequality that you should know by now what the inequality is. It's just putting the inequality in between 2 squiggly lines and putting an X and a line right at the beginning. All right, so interval notation. So when it comes to interval notation, we have square brackets and parentheses. A square bracket indicates that an interval is includes an endpoint. So square brackets indicate that an interval includes an endpoint, and parentheses indicate that an interval doesn't include an endpoint. So when we write interval notation, we do it with the endpoints. If an endpoint has a square bracket, that endpoint is part of the interval. If it has a parentheses, it's going to not be part of the interval. And we'll see what that looks like in a bit. So for an interval that's unbounded at its positive end, or in other words, it's going to the right, it's going towards positive infinity, we're using that symbol, which will be plus infinity, positive infinity. And now for an interval that's unbounded at its negative end or towards the left, that means we're going towards negative infinity. It doesn't stop going towards the left, so we're going towards negative infinity. and we write that as minus infinity or negative infinity. So now we have some descriptions of intervals, and we're going to figure out what type of interval it is, finite or infinite, and then we're going to figure out its inequality, set notation, and interval notation. So for the first row, we have all real numbers from A to B, including A and B. So we see here that we have two endpoints. If I drew this as a number line, I have A and B. I want all real numbers from A to B. So I want everything from A all the way to B, and including A and B. So we fill in those circles because those endpoints are part of the interval as well. So we have two endpoints, and two endpoints tells me that this is finite. So now we need to figure out how to change this description into an inequality. We want all real numbers from A to B, including A and B. So that's some number x in this interval. That x has to be greater than or equal to A, or less than or equal to B. So that x to be part of this interval has to be greater than or equal to A, has to be bounded from right here, including the A, since A is part of the interval. And same thing, we're bounding it to the right side as well. And we're bounding it at B because B is part of the interval. So x has to be greater. If x is part of this interval, it can be any number greater than or equal to A, or less than or equal to B. Set notation, it's just the inequality with the squiggly lines at the end on both sides, and the x and the line. And then we just rewrite the inequality. That's all we're doing. So it says x such that A is less than or equal to x, less than or equal to B. In interval notation, for interval notation, what we do is we want to write the endpoints as an ordered pair. So we start at A and end at B. You write it from least to greatest, so from A to B. And now we need to decide, are they square brackets or parentheses? Remember, square brackets, that means that it's included in the interval. Parentheses means it's not. And since A and B are both part of the interval, they both get square brackets. A is part of the interval, it gets a square bracket. B is part of the interval, it gets a square bracket. Next, we have all real numbers greater than A. So now we need to do the same thing. We have all real numbers greater than A. So we need to see, well, first let's actually do our number line. So we're starting at A, and we want all real numbers greater than A. Every real number greater than A. It doesn't include A, it doesn't say that, it just says every real number greater than A, so every number greater than A, but not including that A. So we only have one endpoint, right? We start at A and we go on forever to positive infinity because we're not bounding to the right side. So we only have one endpoint. That makes this infinite. So our inequality, if we had some x value in this interval, we can say that x is greater than A, right? If we kind of just replace all real numbers with x, we get x greater than A, and that's where our inequality is. X is greater than A. That's how we can describe it on this interval. So set notation, like I said, it's just squiggly lines with an x in the line, and it reads x such that, so x such that x is greater than A. And now we need to do our interval notation. So we look at our interval, the smallest number we have is A, and it goes to positive infinity. So our A, we need to decide if that's going to be a square or parentheses. And since we see that x is going to be any number greater than A, that means our A is not included in our number line. So it's going to be a parentheses. Since A is not part of the interval, it's just everything greater than that A. Now for our infinity, this part is going to be a little tricky to think about at first. So we need to decide, is infinity part of the number line or not? And remember, nothing can actually ever equal infinity since it doesn't have a real value. It just keeps on going forever and ever and ever. It doesn't have a real value. That means we can never actually equal infinity. So that's why infinities always get a parentheses as well. So that's our interval notation for the second row. Now let's go ahead and do the third row. And for the third row, we have all real numbers less than or equal to A. So less than or equal to A. So if we start at A and we want everything less than at A, and we want it to be less than or equal to, since it's equal to, we fill in that A. and that's what our number line is going to look like. Every real number less than or equal to a. And since we only have one endpoint, this is going to be infinite. And if we were to put any x value into this number line, that x would have to be less than or equal to a. That's what inequality is. If you put an x on the number line, that x can be described as being any number less than or equal to a. Or in other words, like we did before, let's erase this. If you replace all real numbers with x less than or equal to a, or x is less than or equal to a, for proper English, whatever it is, x is less than or equal to a. That's our inequality. Now for our set notation, this is the inequality with the squiggly lines and the line. So x such that x is less than or equal to a. Close off that squiggly lines. And now for our interval notation, so our smallest number, that's what goes on the left, is negative infinity, and it goes all the way up to a. So remember what we said before, nothing can actually equal any infinity, positive or negative. So that means the negative infinity gets a parentheses. And our a, since that's part of the graph, we filled in the circle, and it says less than or equal to. So it equals to a, that gets a hard bracket. All right, so let's say you do that. And now for part B, I want you guys to pause the video and actually try it yourselves, and I'll post the answers up in a quick second. So pause it, try it yourself. All right, and this is what you should have done for A, for table A. The inequality, it's a finite interval since we have two endpoints, so it goes from -3 to 2. They're filled in circles, so it's included in the endpoint. And the endpoints are included in the interval, I mean. So x will be greater than or equal to -3 or less than or equal to 2. The set notation is the same thing, but in squiggly lines and the x in the line. Interval notation is square brackets for both sides, since both endpoints are included in the interval. For the second interval, the second finite interval that we have, in this case, it's the same interval, but our -3 is not part of the interval this time in this number line, because -3 is an open circle. So x will be strictly greater than -3, but less than or equal to 2. So our set notation will be the same thing, except we put the squiggly lines and the x and the such that. So x such that -3 is less than x, which is less than or equal to 2. And finally, interval notation will have a parentheses for -3 and a square bracket for 2. Now I want you guys to try B as well. It's pretty much the same thing, except going to be infinite intervals instead of finite intervals. So pause the video again, try it out, and in a quick second, I will be posting answers on the screen, on the video. All right, and this is what you should have done for B. For the first infinite interval, we have x is less than or equal to 2, and it's equal to since the endpoint is part of the interval. For set notation, it's going to be the same inequality, except you put the squiggly lines and the x in the line, so x such that x is less than or equal to 2. Interval notation, it's not very clear, that should be a negative infinity. All right, so interval notation from negative infinity to 2. Negative infinity is a parenthesis since you can never actually equal any type of infinity. And the 2 is part of the interval, so it's a square bracket. For the second one, second infinite interval that we have on the right column, we have x is greater than 2. 2 is not part of the interval this time, so it's strictly x is greater than 2. And what I saw a lot today was that I saw people putting 2 is less than x, and they do equal each other. It means the same thing, but usually you want to be writing it as the variable first. I know usually we always say smallest to greatest, but in this case, you always do with the variable first. That's going to be the one exception. Try to put the variable first when you can. So x is greater than 2. What's the same thing as 2 is less than x? I know it means the same thing, but try to always put it as variable first, all right? So set notation will be every x value such that x is greater than 2. And then finally, the interval notation will be a parentheses on both sides from 2 to infinity, because neither 2 or infinity is part of the interval. So let's keep on going. So now we're going to talk about the interval we have here, and we can see that we're hitting every single possible real number on this interval. So if we were to put this in interval notation, we would have negative infinity to positive infinity. Or in other words, we're going to have every real number, or all real numbers. All real numbers is actually probably the better way to say it. So we're going to say all real numbers. That's all the numbers interval will be all real numbers. So now, what do the intervals 0, 5, 0, 5, and 0, 5 with different endpoints? Sorry, not different endpoints, but different parentheses or square brackets have in common. What makes them different? So, what makes them, what they have in common is that they all have the same numbers inside of the interval. So they all have the same numbers 0 to 5. So every number from 0 to 5. They also have the same endpoints, and they're also finite. So that's what makes them the same. They all have every real number from 0 to 5. They all have the same endpoints, 0 and 5, and they're all finite. That's what makes them the same. But what makes them different is that if the endpoints are included or not. So what makes them different? We'll do that in red. If endpoints are included or not. So for number 3, we're told the symbol U, that YU represents union of two sets. So that's what it stands for. It means the union of two sets. Or in other words, you're kind of just adding the two sets together. So when we have this interval right here, from negative infinity to 0, let's do that in red. So from negative infinity, we have a 0 right here. We go from negative infinity all the way to 0, not including the 0 to parentheses. And then we go from 0 to positive infinity. So 0 to positive infinity starts at 0 and goes to positive infinity. When we add these two sets together, the union of the red and blue lines together gives us our new set, our new interval. All right. So now we need to know what does the notation of this represents. It represents every real number but 0. Right? Because this new interval has every real number but 0. That's because 0 has a soft bracket or parentheses on both intervals that we added together. So let's keep on going. Now we're going to talk about domain and range. So recall that the domain of a function is a set of input values x, or in other words, the domain is all your possible x values, and the range of a function is a set of output values f of x, or all your possible y values, where the graph is going. The end behavior of a function describes what happens to the f of x values or the y values, or really how the graph is going, where it's going, as the x values either increase without bound, and what that means is it's going to positive infinity, or decreases without bound. That says decreases, not very pretty, but decreases without bound or approaches negative infinity. So that's what end behavior is going to be. We're going to look at that in a bit. So let's go on to the next slide. So we have this graph right here, a regular linear function. So we're going to figure out what its end behaviors are. So as x goes to positive infinity, we need to see where the graph or where the y values are going as x increases. As we go to the right of the graph, as x slowly increases, we can see that the f of x, or the graph itself, is increasing. So as x increases to infinity, f of x is also going to infinity as well. And then when we look at x goes to negative infinity, as x is going to the left, we see that the graph is following it going down. So x is going to negative infinity, the f of x or the y values are going to negative infinity as well. These won't always match. This won't always be the case. Sometimes it's going to be different, all right? And if you want to read this little table, you can. I'm not going to spend any time on it. It just says what I just said anyway. So going on to A, we're going to figure out its domain, range, and end behavior. So the graph of the quadratic function f of x equals x squared is shown. That's the u graph we see on the right. We need to figure out its domain. Remember, domain is all your possible x values. So we're going to look at the graph, and we're going to see what are our possible x values. And we can see that this graph goes to the left and to the right forever. It's going to the top left and to the top right. That means it goes to the left and up forever, and the right and up forever. That means it's going to hit every single possible x value. So our inequality will be from negative infinity, which is less than x, which would be less than positive infinity. That's our inequality. Set notation. I'm not going to spend too much time on that. We just talked all about it. That's what it is. It should be a squiggly line out of parentheses. And interval notation, negative infinity to positive infinity with parentheses, since it cannot equal infinity. Now for our range, this is what's going to be a little tricky. Our range, remember, is going to be all our possible y values. So if you look at the graph, we're going to look, our y's are going up and down. So we're going to see where the graph is going up and down. So we see that our smallest possible y value on the graph is 0. We look up and down, the smallest value we see is this y equals 0. And then the graph just goes up, right? It keeps going up this way. So it just keeps going up. So our y value, or inequality, is y is greater than or equal to 0. 0 is part of the graph, so our range is every y value greater than or equal to 0. Set notation, the same thing as the inequality. Interval notation, we go from 0 to positive infinity. Sorry, I don't know if I put parentheses around the 0. It should be a square bracket. So remember, range is every single possible y value on the graph. So start from the lowest y value and see what the biggest one is. Now, end behavior. This one's going to be a little tricky here. Our end behavior is going to be what happens as x goes to infinity, and what happens as x goes to negative infinity. So as x goes to positive infinity, we're going to go back to this graph. So as x is increasing forever to the right to positive infinity, we can see that the graph is going up and to the right. That's the way the graph is going. So we see that x is going to the right, the y's are increasing. As x increases, y is also increasing. So if y is increasing forever, that means that as x is going to positive infinity, our f of x, or really just our y, or where our graph is going, as x is increasing, is also going to positive infinity. But now if we look at what happens to the graph as x goes to negative infinity, or as x is decreasing without bound, it's going to the left forever, we see that the graph is going up. It's also going up. As x is decreasing, the y's, or the f of x, or the graph, whatever you want to call it, they all pretty much mean the same thing. It's going up. The graph is going up as x is going to negative infinity. So as x is going to negative infinity, the y values are also increasing. So as x is going to negative infinity, our f of x, or our y's, are also going to positive infinity. End behavior, you want to see what the end of the y values are going to be, pretty much. How the graph is reacting as x is going to positive infinity or x is going to negative infinity. You can see where it's going. The both graphs on both sides, in this case, are both going to positive infinity as x increases forever, as x decreases forever. All right, for the next one, for B, I want you guys to try that out on your own. So pause the video again, try it yourselves, and in a bit, in a few seconds really, I'll show you the answer. All right, this is what you should have gotten for B. For the domain, you see that the graph goes to the left and to the right forever, so it's all real numbers, negative infinity to positive infinity. The range is every single possible y value. It might be a little tricky to see, but there is an asymptote on 0. What that means is that the graph will never actually touch 0. So the inequality is y is greater than 0. So then, I don't know if y'all have learned about asymptotes or not in the past, but that's what it should be. The graph will never actually hit y equals 0. So that's why inequality is y is greater than 0. And for the end behavior, we see that as x increases to positive infinity, it goes to the right side, the graph is going up to infinity, so f of x is going to positive infinity. I'm not sure why I did this in blue and green as well, but it should be in blue. As as x is going to negative infinity, we see that the graph is going closer and closer to 0. So as x goes to negative infinity, f of x is going to 0. It's getting closer and closer to 0. So when x equals like negative 3 billion or whatever it is, it's still not going to hit 0. It's just getting infinitely closer to 0. As x increases, y will never hit 0. It just gets closer and closer to. That's why it's the end behavior. All right. So what we're going to do now is we're going to reflect why is the end behavior of a quadratic function different than the end behavior of a linear function, and that's just because the y values differ. The end behavior changes because the y values are going to be different. Y values are different, and they're different as x increases and as x decreases. In part B, the f of x values decrease as the x values decrease. So why can you say f of x equals negative infinity as x goes to negative infinity? And we talked about that already. It's just because as x gets closer and closer to negative infinity, as x gets smaller and smaller, the f of x does decrease. It does keep decreasing forever, but it doesn't actually go to negative infinity. It just gets closer and closer to 0. So we talked about that. I'm not going to write that again. It'll be a hassle to write. You just go back in the video if you want to watch that. Number 6, we're going to write the domain and range of the function as inequality using set notation and using interval notation and describe the end behavior of the function. This is actually a good problem for you guys to do on your own. So pause the video and try it out, all right? All right, this is what you should have gotten. D for domain is negative infinity to positive infinity. It's still all real numbers. The range goes from negative infinity all the way up to 0. The smallest y value is negative infinity. The biggest one is 0. And now the end behavior, you can see as x goes to positive infinity, the graph is going down forever. It doesn't have an asymptote, so it keeps going down forever and ever. F of x goes to negative infinity, and x goes to negative infinity. F of x, or the y values of the graph, are also going to negative infinity. All right, we're going to speed this up a bit. This video is long enough as it is. So this is the last slide that we're going to be going over. And what we're saying here is, unless otherwise stated, a function is supposed to assume to have a domain consisting of all real numbers for which the function is defined, or unless we tell you otherwise, unless the function doesn't include it, it's f of x, or sorry, the x value of the domain will be all real numbers. Many functions, such as linear, quadratic, exponential functions, are defined for all real numbers. So the domain, when written in interval notation, is negative infinity to positive infinity. And another way to write the set of real numbers is we draw an R and then put another line there next to the first line. Let's draw that a little better. So you have an R, then you have a second line. When written in set notation, if x is in the set of real numbers, that's what this thing right here means. And it's read set x such that x is an element of the real numbers. All right, so for A, we're told for the given function and domain, draw the graph and identify the range using the same notation as the given domain. So f of x equals 0 for x plus 2 with a domain of negative 4 to 4. So in this case, we limited the domain. So what we have here is, since we're limiting the f of x, since f of x equals 0 for x plus 2 is a linear function, the graph is a line segment. We see that on the right. And we have its endpoints right here and here. And so we can see that the range, we have the domain, negative 4 to 4, but the range is going to be the smallest y value, which we see is negative 1. And that's part of the graph. It is a filled in circle. And the biggest y value here that we see is 5. That's also part of the graph. So we put a square bracket as well. I think I said square bracket for negative 1. That's what it should be. That's what the answer is. And that's finally the end of the video. It's been a very long video. If you watch this whole video, I am impressed. I would have been bored listening to my voice by now, but hopefully it helped. Hopefully you learned something, guys. And that's going to be it for the video.